In this video, we're going to discuss half-life, which is the amount of time that it takes for a radioactive sample to undergo decay. For example, carbon-14 is a radioactive element. It has 8 neutrons and 6 protons. That's one too many neutrons for it to be stable. So it's going to undergo beta decay so that one of those neutrons splits into a proton and electron. The electron is given off as the beta particle, and we're left with a mass of 14 and an atomic number of 7. So the neutron splits into a proton and electron. The extra proton stays in the nucleus, and now it is nitrogen, which is going to be stable. So if we started with 100 grams of carbon-14, the half-life is the length of time that it's going to take for that 100 grams to decay into nitrogen such that only 50 grams of the initial carbon is left. For carbon-14, this time is about 5,730 years. So a very long time. Some half-lives are very long, others can be very short. Up here from the previous notes, whenever we have radioactive decay, you might have heard of a Geiger counter. It's that box-looking thing that makes all the clicking noise. I recommend you check one out while you're watching this video, just to see what they look like and sound like. Anyway, they measure the radioactivity in the air. Also, you can use a canary, but as they might be limited, Geiger counters are used. So half-life of thorium-234 is 24.1 days, meaning every 24.1 days, half of any sample of thorium will be gone. So 24 days represents one half-life. So just HL for short. So in 24.1 days, half of our original sample will be gone. 48.2 days would represent two half-lives. So half of a half is a quarter. After 72.3 days, this was 2 half-lives. This represents 3 half-lives. So a half of a quarter is 1/8. And then finally, after 4 half-lives, you would have a 16th. So every half-life, whatever that time frame is, half of your original sample will be gone. Uranium, you can see its half-life is on the order of 10 to the 9th years, so it takes a very long time for uranium to decay into something that is stable. We're going to skip this particular calculation because you're better served with more specific examples. So in all these half-life problems, there are going to be a couple different variables, all which work together. For the most part, we're going to cut the higher mass in half, which will be our starting amount, the correct number of half-lives until we get to the lower mass. We're going to use arrows to represent the half-life, and you'll see that when we get to our example problems right now. So we have a 200 gram sample of some generic radioactive substance. We allow it to decay. In 30 minutes, 25 grams of the substance will remain. We want to know how long its half-life is. So, as you're starting to see these for the first time, I recommend writing everything down. We're going to have a starting amount, which is 200 grams. That's how much of the material we start with. Since we have a starting amount, we're also going to have an ending amount. This is going to be how much is left. We have 25 grams left at the end. So 200 grams of this radioactive substance will decay into 25 grams. We also have our total time. In this case, 30 minutes is allowed to occur. You might refer to this as elapsed time as well. Same thing. So this is 30 minutes. Please make sure that you include the appropriate units with these time frames, because some will be minutes, some will be seconds, others will be hours, years, days. The unit matters. At the end, we want to know what the half-life is. So I typically abbreviate that T sub 1/2. So this 1/2 is subscripted, hence T sub 1/2 just means the time for the half-life. We don't know what it is in this case, so we're going to put a question mark. Another variable we're going to be concerned about is the number of half-lives. So this is how many times it divides in half. We don't know that yet either. What relates these times is that the number of half-lives equals the total time divided by the time for one half-life. And you'll see how this works in a minute. So we know we're going to start with 200 grams. After one half-life, whatever that time frame is, how much will be left? 100 grams, because that's how half-life is defined. We have not yet reached the correct ending amount, so we know that this 100 grams is allowed enough time to cut in half again. So now it is down to 50 grams. Still not the correct ending amount, so we allow it to divide in half one more time, and we get 25 grams. So looking back, it took us 1, 2, 3 half-lives to go from 200 grams down to 25 grams. We had to cut our starting amount in half 3 times. So in this case, if the total time was 30 minutes, and during that 30-minute time frame we went through 3 half-lives, what is the length of one half-life? Obviously, it would be 10 minutes. 10 minutes here, 10 minutes there, and 10 minutes there. Such that our half-life time, just working this algebra, T sub 1/2 is going to equal the total time over the number of half-lives. Just HL for short. So our total time was 30 minutes. We know it underwent 1, 2, 3 half-lives, counting the arrows. So that gives us 10 minutes per half-life. So 10 minutes would be the length of our half-life. Every 10 minutes, half of the sample will be gone. Let's do another one. Exact same type, looking for the half-life. We start with 500 grams. We're going to end with 31.25. We know we're going to allow it to decay for 24 days, so that is our total time. We don't know the number of half-lives yet, but anytime you have both the starting and ending, that will necessarily allow you to calculate how many times it goes through the half-life. So we start with our 500. We're going to draw arrows, cutting this value in half until we get down to our ending amount. So for some of these, the math is easy, straightforward. Others, you might have to work at it a little bit. So 500 divided by 2 is 250. We're not at the end yet, so we're going to keep going. So we get to 125. Half of 125 is 62.5. Still not there yet. One more, 31.25. If you can't do that math, just do it in your calculator. 500 divided by 2, divided by 2, and you can keep pressing enter as many times as you need until you get to your answer. So in this case, we went through 1, 2, 3, 4 half-lives as represented by our arrows. So that is 4 half-lives. If our total time is 24 days, and in those 24 days we went through 4 half-lives, the time for one half-life, 24 over 4, equals 6 days. So this was 6 days, 12 days, 18 days, 24 days. Okay, finally a different example. Here I give you the half-life, telling you that it's 25 days. So half-life equals, represent that with our T1/2, half-life equals 25 days. We're going to start with 500 grams. And we want to know how much remains after 100 days. So in this case, we don't know the ending amount. Ending equals unknown. We know that our total time is going to be 100 days. So this is slightly different, but remember from our first slide, I wrote that the half-life, or the number of half-lives, equals our total time divided by the length of one half-life. So if we have 100 days total, and every 25 days the sample will divide in half, how many half-lives will occur during that 100 days? Obviously it should be 100 days total divided by 25 days per half-life, and that gives you 4 half-lives. In the previous problem, we cut our starting amount in half to get our half-lives. In this case, we're looking at the comparison of the times. It's always going to be the longer time, the total elapsed time, divided by the time of one half-life. So we should always get some whole number here. I wouldn't give you a problem where you get a decimal. But maybe I will. I don't remember. Moving on. So in this case, now that we have this 4 half-lives, that doesn't answer our question. We want to know how much is left. So now that we have this information, we know we have to cut our starting amount in half 4 times. So we start with 500. Cutting in half once gives us 250. So these were the same number progression as last time. One more time gives us 125. One more time, 62.5. And once again, we get to 31.25 grams. So exact same numbers as before. So the half-lives were slightly different. Different approaches, but all using the same information. We could also do this backwards, where I could give you the ending amount. Like, let's say I told you that at the end of 100 days, 31.25 grams was remaining. So let's say we don't know all of this. We're going to end with 31.25. And we wanted to know how much we started with. Once you got the number of half-lives, being 4, you could just work backwards. But instead of dividing by 2, like you do from the start, here you would just multiply by 2. So this times 2 would have given us 62.5, times 2 again would be 125, the third time 250, and then finally 500. So if you're given the starting amount, we're going to cut it in half. If we're giving the ending amount, we could double it to get back to our starting amount, just depending on the way you're going. You could also see this graphically. In this case, we have the mass of the substance remaining, and here we have the time frame. So in this case, we want to look at the time frame that it takes for the substance to be divided in half. So this value, it's hard to see with the label here, that is 120. This mass here is 60, and then this mass here is between the 20 and 40, so that's 30. So it looks like this gets cut in half every 2 days. So here the half-life would be 2 days graphically. So we'll do more practice with this in class. Let me know if you have questions.